In this nutshell, I look at the on-chip peripheral interrupts. I describe what they are. Then I look at both the ADC and the USART, how to enable the interrupts in the registers, and I give programming examples. And if you find this video useful, please like and subscribe. We have looked at the external interrupts, which are triggered by an event happening on an external pin. There are also peripheral interrupts. So these are linked to the hardware modules inside the microcontroller, such as a timer, UART, etc. And they will generate an interrupt when a hardware event occurs, such as an ADC conversion complete occurs. So each peripheral has two key control bits: interrupt enable, that turns the interrupts on for that module, and interrupt flag. This is set by hardware when the interrupt condition occurs. So for an interrupt to occur or execute, three conditions must be met. You must enable the peripheral interrupt, you must enable the global interrupts, and a hardware event must occur. You can also determine if a hardware event occurs by looking at the interrupt flag. You can poll it manually. And this is just a separate way of dealing with events happening on your peripheral devices. So looking now at the onboard ADC. If we are using interrupts, then when they are enabled, when a conversion is completed, the ADC interrupt service routine should be called. The ISR should store the result register and update the channel for the next ADC reading. Now, if you are using interrupts, you're best using it for multiple channels. If you're only looking at one channel, then it's probably best to use the free running mode. The register associated with the interrupts is the ADC control and status register A, and we are looking at bits 4 and 3. So bit 3 is used to enable or disable the interrupt, writing a 1 to enable the interrupt, and note global interrupts must be enabled for the interrupt to occur. Now you can use the ADC interrupt flag register. It's set by hardware when the conversion is completed. It's cleared when the interrupt service routine is finished, or writing a 1 to this bit. So you can use the flag as a polling rather than using interrupts. Looking at some example code, I'm just showing you the interrupt service routine here. Once again, the ISR is called when the ADC conversion is completed. I'm using a switch statement to select what action to take. The case inside the switch statement stores the ADC result, reloads the ATmega with the next channel, starts a new conversion, and updates the state variable to move to the new case. And of course, after the break, we exit the switch statement and exit the interrupt service routine. So basically, looking at this here, I define the channels, the ADC 0, 1, and 2, the start conversion, and I'm using a switch statement inside the interrupt service routine. So this is called every time the conversion has been completed. So assuming that the state is 0, then I store the result register into my variable temperature 0. I then update the channel to look at ADC 1, that's looking at ATmega. I start the conversion, and then I change the state variable to 1. The break takes me out of the switch statement and then out of the interrupt service routine. So now when I come back into this routine, the state is 1, and I then go through and store the temperature 1, update the channel to ADC 2, start conversion, state goes to 2. This is repeated. In case 2, I store temperature 2, update to ADC 0, and so on. So basically, I can then use the variables temperature 0, temperature 1, temperature 2 in my code, and they will be automatically being updated by the interrupt service routine shown here. Looking at an example of the ADC using interrupts, we have some code that reads the value of 2 pots on the megaPro board and display the value of these pots onto the display. The structure diagram shown here, we have the setup, a while 1, and the while 1 we output pot 1 and pot 2 to the display. In the setup, we set up the ADC and the display itself. In the interrupt service routine, we come into this routine whenever a conversion is complete, and we use a switch statement to store the results of channel 1 and channel 2 into the variables pot 1, pot 2. Looking at the code here, we are using interrupts, so we must include the interrupt.h library. Also, the display driver needs the standard IO, string, and display driver.h libraries. So we dividing pot 1 channel 1 and pot 2 channel 2. This is used within the ATmega to select the channel. So bits 7 and 6 are used to select the reference. Bit 5 is set to a 0, and that will make the result register right aligned, so that's used for 10 bits. And these last 5 bits here, bits 4 to 0, select either channel 1 or channel 2. We configure start ADC. Looking at the variables here, we're using pot 1 and pot 2 as ints because they are 10-bit results. We have a setup while 1. Now this function simply outputs pot 1 to the display and pot 2. They are being updated in the interrupt service routine. The setup here, we initialize the display, and finally we're setting up the ADC SRA register. Bit 7 turns on the ADC. Bit 6 starts the first conversion. Bit 5 is 0, which makes it single conversion mode. Bit 3 enables the interrupts on the ADC, and these last bits select the conversion speed. Looking at the actual interrupt service routine itself, remember we come into this routine every time a conversion is complete. We're using a switch statement. Initially state is 0, so we come into here, we store the result of the channel 1 conversion into pot 1. We send the mux for the channel 2. We start the ADC, and the state is set to a 1. We exit the interrupt service routine. When another conversion is complete, we come back into it. We're now state is case 1. So then we store the result of the channel 2 conversion into pot 2. We select the ATmega to channel 1, start the ADC, and set the state back to 0. So this will repeat, updating both pot 1 and pot 2. So I've written that code into Microchip Studio, and we can download it to the megaPro board and see it running. Expand that out. Here's the megaPro board in action. Here's pot 2, and we can adjust pot 2 and get it up to the full value. Similarly, we can adjust pot 1 and get that working as well. So we are using interrupts to read the 2 pots and output that to the display. Now looking at the USART and the interrupts that it has 3 interrupts within the system. We have receive complete. An interrupt will occur when a new byte of data has been received. Transmit complete, an interrupt will occur when both the transmit data buffer and transmit shift register are empty and the data register is empty. And that will cause an interrupt when the USART data register is empty. That's the transmit register. Note, global interrupts need to be enabled for any interrupt to occur. So just looking at those interrupts again, basically when we receive a byte of data and it's placed into the receive register, if the interrupts are enabled, you'll get an interrupt when the buffer register is full. For the data register empty, this is the transmit. When this register becomes empty, that will cause an interrupt. And finally, transmit complete. This is when both the UDR transmit register and the transmit shift register are both empty, which means all the data has been fed out of the transmitter. You normally use that interrupt to power down the transmitter after all the data has been sent. So these interrupts are enabled in the UCSR-NB register. Bit 7 will enable the receive complete, bit 6 will enable the transmit complete, and bit 5 will enable the USART data register empty. Looking at an example of using the USART interrupts, I have written some code here that uses both the receive complete and the transmit data register empty interrupts. So we're using the loopback feature of the megaPro board, where the USART transmitter output is connected back into the USART receiver input. Looking at the state diagram, we set up the onboard devices. We have a while one loop here, and we are basically incrementing count every 500 milliseconds. In the setup, we set up both the UART and the GPIO. The interrupts we're using are the transmit buffer empty, UDR empty, or the receive complete, the receive buffer is full. In the UDR empty, we simply load count into the data register. That will transmit the count value out. In the interrupt receive register, when we receive data, we store that into port C. So looking at the code, we are using a delay routine, so we need to configure the CPU frequency. We're using the interrupts, so we need to include the interrupt.h library, and we're using the delay.h library. We can see our main loop here, set up while one, increment count every 500 milliseconds. Scrolling down and looking at the code, we're setting up the general purpose I/O. So we are setting port C for output. We are configuring bit 2 and 1 for loopback and the transmit out. We're turning on the loopback switch. Now the board registers, they are explained in previous nutshell, so I won't show that here. The main thing we're looking at is that we are enabling the receive complete interrupt and the data register interrupt shown here. So that's the two bits I'm interested in, and we are enabling global interrupts. So whenever we get new data received into the UART, we load that into port C, and whenever the transmit buffer is empty, then we load count into the buffer into the data register, which will send the data out. I have written that code into Microchip Studio, and we can download it and see it running. So therefore, the count is being incremented, sent out the transmitter. We've got the loopback going, and so therefore the count's coming back into the receiver and displayed on the output port C. So that's the main structure of the code there. We transmit the count out, and then we receive it onto port C, while one only has C count code. Example of the USART interrupts. There's some code written here which is a null character remover. We have some data which is being received into the UART. We check to make sure the character is not 0. If it's not 0, we echo it back out the transmitter. So the data stream is just going through. If, however, we find a 0 in the character, we don't send it. So it's stripping the null characters. So in the code below, we have a while 1, nothing in there. In the receive complete interrupt, when a byte is received, we load that byte into a variable, receive data. If the received data is not 0, then we enable the transmit buffer empty register. When that transmit buffer is enabled, then we will transmit the received data out, and will disable the transmitter so no more bytes are transmitted. Looking at the code itself, we're including the interrupt service .h library for the interrupts, and then looking on the USART2B register, we enable the interrupts by setting this bit to a 1, and we disable the transmit buffer empty register by clearing it. The main loop here, the while one has nothing. Inside the setup, we set up the baud rate, odd parity, 2 stop bits, 8 data bits. And the main thing here is we are enabling the receive buffer register full. And then in the interrupts, if we receive some data, we store and receive data. If the received data is not 0, then we enable the transmit buffer empty interrupt. Inside the interrupt, we transmit the data, and then we disable the interrupt. So that's the null character remover shown with the receive buffer full and transmit buffer empty interrupts.